Hello, my name is Gyubin Kim and this is my presentation for Lab 4. This is the presentation order. I will start from the introduction, brief preview, computational model, results and observations, and discussion questions as the final part. The purpose of this lab is to observe the magnet falling through a conductive tube of aluminum foil. We will use a computational model of the magnet falling and find out how long that takes, and compare with the experimental value. The assumptions made here are, first, air resistance is negligible, second, that the north end is pointing down when falling, and 3, that the aluminum foil tube is non-ferrous. The reason why we use non-ferrous material is because ferrous materials interfere with its own magnetic field. There are a total of 6 main principles utilized in this experiment. First is Faraday's and Lenz's law, which describes the magnetic flux that changes in time, which creates a non-Coulomb electric field that generates a voltage. Viot-Savart law describes the magnetic field generated by constant electric current. Magnetic flux in this experiment describes a measure of how much magnetic field passes through an area. Magnetic force describes the force made by magnetic pole. Newton's second and third law describes that force equals mass times acceleration, and amount of force equals the amount of reaction. Lastly, Ohm's law describes the relationship between voltage, current, and resistance. In the experiment, the system is the magnet while surroundings are everything excluding the magnet. Initial conditions were that the magnet was held above the tube and there are no external forces acting on the system. Procedure was simple: drop the magnet, record the time, and repeat that 5 times. And I could observe that the magnet took a longer time to fall compared to falling in free space. The possible source of error is human error while recording the time it took for the magnet to fall. This is the brief preview of the experiment. It took approximately 1.53 seconds for the magnet to fall, while it should have taken only 1.503 seconds computationally. This is the computational model used to calculate the 1.503 seconds. In the first oval, the constants were plugged in. In the second oval, the height, width, and inner radius of the aluminum foil was plugged in. In the third oval, the mass of the magnet and the magnitude of magnetic dipole moment was plugged in. In the fourth oval, Viot-Savart law was typed in. And in the next page, in this area, circled in this oval, is to calculate the flux of the magnetic flux. The sixth oval calculates the current using the Faraday's law and Ohm's law. An equation to find the magnetic source was utilized in the last oval to calculate the net magnetic force on the magnet. This is the end result of my code. I found that red represents counterclockwise and blue represents clockwise using Lenz's law. The process is explained down here. When the magnet is flipped upside down, there will be no change, but the magnetic field of the magnet and induced points will change. The result from code is shorter than the time from experiment due to not regarding air resistance, and there should be a part in code which takes air resistance in account to make the result more realistic. Lastly, the sharp decrease in the beginning and at the end explains the time where magnetic force is less than the gravitational force, and the straight lines indicate that those two forces are balanced out. The first what-if question asked us what would happen if the resistivity of the conductor were reduced as close to possible to 0 and the change of dynamics of the falling magnet. In this case, the induced current would increase, leading the magnetic force to increase as well. Thus, the magnet would fall slower. This is all based on Ohm's rule. The second what-if question asks what would happen if the tube had holes or slots. Holes or slots in the tube would decrease the induced current, and Lenz's law would not be useful to analyze the observation in this case. This would lead the magnetic force to decrease as well, thus making the magnet fall faster. And that is all of my presentation for today. Thank you for listening.